Okay, I think we can begin now. So my name is Dr. Neil Cagney. I'm a lecturer here within Aerospace, and I'm also the Director of Admissions for the school. So the point of this talk is just to give an introduction to aerospace at Queen Mary. So what it involves, what the discipline of aerospace involves, what it's like learning at Queen Mary, what the actual course structure is like, and then kind of a little bit on the graduate attributes. The opportunities for graduates from here. So that's just what is summarized there. So what is aerospace engineering? We're going to talk a little bit about aerospace in Queen Mary, as well as what you'll study. I'll give a kind of brief introduction to the student projects, and then also we'll talk about the careers and opportunities. So firstly, what is aerospace? So what everyone normally kind of thinks about when they think of aerospace is basically the 5 things you see here. So on the left, you've got aviation. That could be civilian aviation, like the kind of BA plane there, or it could be defense. So in those cases, you're talking more kind of supersonic, more kind of high performance. Aerospace. So there's also space systems. That could be rockets. That could be the type of things that are, SpaceX is producing, or it could be satellite systems that often involve a lot of neat robotics and kind of energy systems. So it could be those. And then also, kind of more broadly, is when you think of something being aerodynamical, you think of it, how it relates to the air flowing past it, and that would be relevant often in the automotive industry. So that could be, a lot of the students are very interested in Formula One, but then there's also a lot of kind of stuff like, your kind of family cars and that sort of thing, and there's a huge range of jobs in the UK in both those sectors. But aerospace encompasses a huge amount more. So one of obviously the growing sectors over the last couple of decades, and we know is going to continue to grow, is the green or sustainable energy. So just a couple of examples here: wind energy, tidal energy, and that's particularly a gas or a nuclear power plant. If you look at just the wind turbines, they're essentially just, each of those turbines is just comprised of 3 wings. Now they rotate like a propeller as opposed to just kind of flying straight like a wing. The design principles are exactly the same. If you've got any type of power system, what generally involves is either burning a fuel, turning water into steam, passing that steam through a turbine, and taking that kind of rotational energy. So it's essentially like a wind turbine. Again, different design constraints, but the overriding principle is it's just aerospace, it's aviation, it's that flow past wings, past turbine blades that makes them rotate. So aerospace is central to energy systems. It's also central to buildings and kind of civil architecture. So this is an example here that's a computer simulation of flow past the Shard in London Bridge. And what you see here is you've got the kind of, these lines represent individual kind of paths that little bits of wind might take. And you see them kind of swirling around behind. They're flowing from left to right, and they're swirling around behind the Shard. Now, where this becomes interesting is you can get, say, you have a block of flats behind, and you get the air kind of whipping around the structure and kind of buffeting into the windows. It can also create things like gusts at ground level. There's a particular problem in the walkie-talkie in East London, where it can be quite dangerous for pedestrians. So whenever you have a large design project, you would also get aerospace engineers in to understand the flow of air. One of the elements that's been quite relevant in recent years is disease spread. So these slides were made during the pandemic. And one of the work that a lot of us within the aerospace department were working on was COVID spread. So the way it spreads is through tiny droplets or large droplets. Tiny droplets drift with the air, large droplets kind of is moving ballistic, essentially like a missile, just fires out. And as you can see in this little visualization of this man giving a big hearty sneeze. The way these things move about is it's aerospace, it's aviation, it's fluid mechanics, it's just them drifting through the air and how the air interacts with them. And it's exactly the same principles as you might study, a rocket or a missile or whatever moving through the air. So the whole kind of core concept of where diseases like COVID or flu or the cold or anything like that spread is essentially aerospace as well. One of the areas I'm quite interested in is in sports aerodynamics. So in this case, they're doing some experimental modeling of the airflow past an Adidas football. And there's a huge amount of work into understanding how the way the various sports balls are designed that can improve performance. So one example was from the 2010 World Cup in South Africa. They introduced a new football, and when they played the actual tournament, they found it kind of swerved kind of chaotically. And what had happened was they had thought, okay, by sealing it better, by removing all the stitches and making it extra smooth, we'll get better play. In fact, what they found was it caused it to swerve, and they hadn't really understood the aerodynamics of it. So the point of just these slides was just to kind of give a scope of that aerospace. You're not just locked into some of the classic things we think of with aerospace. So we're not just locked into aviation or space or kind of all the automotive design. There's a huge range of different kind of potential sectors you can move into with an aerospace degree. Now, if you do go into kind of maybe the more classic kind of sense of aerospace, what are some of the things you could be working on? There's essentially three different kind of sectors. One is experiments. So that's, for example, you're working with Boeing, you're designing the latest generation of plane. It's constructing things, it's physically testing things in wind tunnels. There's different ways you can do that. So that could be taking test flights, which is the image shown at the bottom right, or it could just be doing wind tunnel measurements. And it's reading this data and trying to process it and trying to kind of test out the designs. One of the massively growing sectors is computer simulations. Now, if you've got, say, for example, a new wind turbine design, 100 meters high, 50-meter diameter, it's not practical that you would be making test models each time, installing it at a cost of millions, and then testing it, and then scrapping the design, starting again. In fact, what we do now is we create computer models, and like this one here, where these would be kind of very high-end ones, so they'd be run on supercomputers, and they'd be done in kind of collaboration. They're very large jobs. That's essentially the way it works now, and we do cover this stuff in the kind of later years of the degree. We'll talk about that again later. And just some other examples here. There's the fighter jets, the Formula One car, but it's used in kind of all sectors. How this would work in practice is you generally, something that's not shown here, is work with design engineers. So essentially, the whole process of how kind of design takes place will be design engineers will come up with something, a new design, that gets tested with the computer simulations. And the computer simulations are great, but we can't really trust them until we've got experiments to go with them. So the experimentalists and the computer simulation people work together to kind of test out the new designs. They might kind of give guidance, link back with the design engineers, and the design engineers will generate the next generation of designs. And so that's kind of the whole kind of basic principle of what the majority of jobs are within aerospace. Computer simulations is probably the largest, followed by design, and the experimentalists, relatively smaller amount. Now I'll just talk a little bit about aerospace within Queen Mary. So just a little bit about the aerospace division here. The aerospace department was set up in 1907, 1908. That means it's the oldest aerospace department in the UK, and arguably the oldest in the world. So for context, the Wright brothers flight was just a few years before, I think in 1904. So we're really right at the cusp of when it started. We're fully accredited by the Royal Aeronautical Society and the Institute of Mechanical Engineers. Now, what that means is that these are kind of UK-wide bodies of kind of engineers, of mechanical or aerospace engineers, and they've come in, they've gone through our entire kind of teaching program and just given it the stamp of approval that this is a high quality degree that will be respected anywhere in the world. And just on the right here is the Aeronautical Journal. That's a scientific or an engineering research journal. It's one of the most kind of prominent ones within aerospace research. And this was a centenary issue they did to mark the 100th anniversary of the department here in Queen Mary. I want to talk a little bit about the facilities we have. So this is just a shot of some of the wind tunnel space we have. So there's a large wind tunnel here. So I'm not sure if you can see my cursor, but it's the yellow structure there. Now that's only showing about half of it. It goes across, and then there's an entire other section kind of underneath. So that gets wind speeds up to about 40 meters per second, so about 100 miles an hour. The test section with these two people are at is about 1 meter by 1 meter square, so you can get quite large models in there and really test them to quite high speeds. These are the students use these within their second year, and then potentially in third year they use them for project work as well. I'll talk about that a little bit more later. There's another wind tunnel that's unfortunately kind of out of shot, so behind the kind of underneath that kind of mezzanine floor. Again, it gets wind speeds up to about kind of 80, 90 miles an hour. It's used for undergraduate work or student projects. Now, there's several just on the top here. There's several smaller wind tunnels. These are things for measuring the forces and stuff you can place in the wind tunnel, measuring pressures, doing kind of smoke visualization. If you come to some of the opera holder days, you might get a demonstration of these. And these are used extensively throughout the second semester, first year, and then also in your second and third year as well. There is a flight simulator. This is soon going to be out of date. We've commissioned and have bought a new one, which will be installed in the coming months. So it's larger, it's got greater kind of adaptability. I'll talk about that again in a couple of minutes. And there's another even larger wind tunnel that again can go up to about 100 meters, 100 miles an hour. And that's kind of out of shot there. We also have the series of supersonic tunnels. So supersonic meaning going faster than the speed of sound. We have 3 of the main tunnels. So we've 2 shown on the top. One of them is shown on the top left there. That can go up to Mach 3s, 3 times the speed of sound. So in that case, the air is going at about 1 kilometer a second. We've also got a transonic one on the top right. So in that case, it's looking at the wind speeds just below supersonic, which is where a lot of kind of civilian aircraft operate. We can do various things. We can measure the forces and things within the wind tunnels, measure the pressure distributions. So, you know, if you've got the nose of the plane, which is, you know, for example, shown on the left there, bottom left, you can look at the shock waves created by the supersonic flow and also the effect of that supersonic flow on the structure. We're also interested in, we've got some facilities for doing supersonic acoustics. Now, any of you have ever experienced a supersonic boom, you'll know for one thing it's very loud. And so, for example, when there was the Concorde, which was a civilian jet that flew back and forth from the UK to the US, one of the reasons it went out of business, one of a couple of reasons, is just it was no longer economical, and partly that was because they couldn't fly at supersonic speeds over land because just the noise was too high. So what some of this research is about is we've got this aneroic chamber and it's blasting air out of a nozzle at supersonic speed, so replicating what you would get in the jet engine of something like a Concorde or a fighter jet or something, and I'm trying to understand how we can minimize that noise. Now, this is a bit more in-depth look at the flight simulator. Now, again, this is up to date, but will soon be out of date once we get the new system in. So this is just it operating. There's a student in there. That's what the student can see. It's a replica of a full cockpit. And as they're kind of turning, you can see the hydraulic system that's mounting the flight simulator is also kind of turning to reflect that. Now, the new system will have a greater range of, essentially it's open source, so we can upload any kind of properties for any different type of jet or plane, be it civilian or defense. It has greater kind of hydraulics, so it can really replicate the movement more, and it's larger, so we can get multiple students in at a given time. So this is used in some of the flight and stability modules you can do in second and third year. I'll talk about that again later. And it's also used in research projects. Students also get, in their second year, during one of the flight and stability modules, again, which I'll talk about later, students actually get taken up in for an extreme flight course at Cranfield. Now, what this involves is throughout the module, you learn about different kind of flight conditions. So basically how you can kind of end up in dangerous conditions where, say, for example, the plane starts to wobble or pitch, and the pilot actions that would be needed to kind of maintain safe flight, and also what type of control system you would need to kind of maintain that safe flight throughout. Now, with this extreme flight course, it would normally be taken by pilots. So they're kind of getting themselves into these unstable or dangerous flight conditions and then stabilizing themselves. And what will be happening in this case is you get students all going into the cabin, the plane, and as shown on the left, the pilot kind of gets into these stable conditions and unstable conditions. It's fully instrumented, so you're tracking all the kind of the altitude, speed, your kind of pitch angles, all this stuff, and then that data is all taken back, and the students would normally complete an assignment based on that. We also have a series of supercomputers. Now, what this is replicating here is something called bird strike. Now, if you've got a small plane, say something like a small Cessna, a kind of propeller plane, maybe 4, 8, 6, 8 seats, something like that scale. One of the risks with these planes is this bird strike, which is when a bird kind of hits into the wing. You might think it's a large plane, it should just be able to withstand that, but you really need with planes to try and keep the weight down as much as possible. So, for example, if you have a civilian plane, say a jet that's going to be flying across to back and forth to France, say, that might operate for 20, 30 years. Any additional 10 kilograms of weight that you take, you lift up and you land and you fly that 10 kilograms 4 times a day, every day of the year for 30 years. The cost of that in fuel at the end is huge. So any saving you can make is absolutely massive. So the other kind of thing you might think is, okay, we'll just get really expensive materials, just get really titanium, the whole thing out is titanium, really strong. Factory can't really do that because then the cost would be too high. It's just not economical. So instead, what we have to do is we have to be really careful or clever with how we design things. So we use the minimum amount of material, we get sufficient strength without using super expensive material, and we also keep it lightweight. What this project was looking at was modeling bird strike, which is specifically focused on how do you build something that is light, it's stable, but it's also strong enough to withstand an impact. And with the preliminary work is shown on the left. So instead of modeling, a goose or a bird or a swan or whatever with the beak and wings and all that, it's just simplified down into a little kind of bullet-shaped thing. And that's it kind of impacting on a wall. And then the video I'm going to show on the right is looking at the impact into the wing. And then we're going to look at the structures within the wing to see how they're kind of deforming and how they're holding up. So that's the bird impacting. It's kind of birds essentially splattering. You can see the kind of wing crumpling a little. And next we're going to get a look inside to see how the internal structure has withstood. So you can see it's got these girders inside, and you can see that the front one has kind of bowed, but it hasn't broken in. So that's that, and that gives a reflection of sort of some of the work that a design engineer might do, of kind of that mixture of understanding the mechanics of solids, so how the materials use, understanding the choice of the different material properties you need to have, understanding how you cleverly use things, so design, and using, say, computer simulations to kind of, and that computational side to really probe that. So what you study, if you, sorry, excuse that. Each year is divided into 2 semesters, so essentially before Christmas and after Christmas. Within each semester, you take 4 modules. Now, in many of these ones, you share them with the other streams. You share them with the mechanicals or the kind of chemical engineers or whatever. And then the ones highlighted in yellow are the ones that have a specific aerospace component. I'll talk about each of these. Now, the first thing I want to talk about is computational maths and modeling. So it's split into 2, statics and dynamics. Now, what these essentially are, they're kind of a maths module. You need to have, in any engineering degree, one of the reasons why engineers are in such high demand in the kind of job market is because they've got a a solid foundation of maths. So you will use maths throughout all modules, but you really get a foundation for that in your first year in these two modules. We've kind of combined that with a bit of kind of physics and mechanics. So the first one is using maths, but applying it to static problems. So that's structures that aren't moving. And then dynamics is the second one, where things are moving more. That's probably more relevant to aerospace, where, in this case, the air is moving. Both of these, the computational part also involves computer coding. So the way undergrad programs were traditionally structured was that you would learn little different bits of code in different modules, depending on the preferences of each individual lecturer. We decided to scrap that, so you're going to consistently build up, and so the whole program, that the second year modules build on the kind of bits of coding you learned in the first year. So in this case, we've chosen to opt for Python because it's used a lot in industry. It's used a lot by kind of engineering employers, and yeah, it's readily available for you to work on, both kind of within this course and, if you want to continue developing that outside. So you use kind of the maths is combined with this computer programming. You also have engineering design. As we'll see again, we have kind of design will pop up again and again each year. I've spoken a little bit about the importance of that. I also spoke a little bit about the importance of choosing materials. So kind of finding things that are economical, so not too expensive, they're not too heavy, they're sufficiently strong that can withstand whatever you need. What stuff you can do to kind of improve material properties? What are the material properties we care about? What are the ones we need to prioritize when we're kind of choosing materials? And that kind of fits in with the design, and it also fits in with the, say, for example, that example I gave just a minute ago of the bird strike and the wind. Now, you'll also see there's two modules here on the right, Experimental Design and Practice 1 and 2. Now, again, traditionally, the way engineering programs was taught were, you do 8 modules and you do a little bit of experiments in each, and it kind of structured around basically what was available, to use and how we can crowbar that in. We, again, scrapped that approach, and we decided we're going to take all the experiments, we're going to put them in one module. One in semester A and another one in semester B. The benefits here are that you're gradually building up not just your experimental skills, your understanding of how to use measurements, how to use wind tunnels, how to use kind of other measurement devices, but also you're building up your skills in teamwork, in presentation skills, and report writing skills. So it's building up that soft skills. And one of the things that's great about is if you're applying, say, for students kind of summer internships after your first year or your second year, you've got all this stuff to kind of point to on your CV of all these soft skills that you've developed. Likewise, by learning Python, you've got that to put in your CV as well. The reason the bottom right one is highlighted in yellow, Experimental Design and Practice 2 in semester B, is because that is that's where you start to use the wind tunnels more. So in that case, you'll take some of the course shared with all the different streams, your chemical engineers, your mechanical engineers. But in semester B, the aerospace students branch off and they do a series of projects just looking at the wind tunnels. There's thermofluids here, which might be a confusing name. It's a shortened form of thermodynamics and fluid mechanics. Thermodynamics is essentially how you turn something like a fuel or a liquid into work or power. Essentially, that's stuff you would use in kind of engines, be that jet engines or kind of combustion engines that you might get in a car, say. And the majority of that is fluid mechanics. Now, fluid mechanics, when you say fluid, we mean that can be any liquid or gas. So essentially where that's relevant to us is, as kind of aerospace engineers, it's the flow of air over a wing or any other kind of structure like that. So essentially, this is your first step of your kind of introduction into the science of aerospace. So in this, say, for example, you start to learn things about like how a wing works, what are the factors you would need to take in, what are the aerodynamic forces you need to care about when designing planes, how we predict those, how we calculate those, how we anticipate those. That module is taught by myself, the fluid mechanics part is taught by myself. And lastly, we have exploring aerospace. Now, because some of the first year modules is kind of, a lot of it is laying the groundwork, developing the skills, like the math skills you'll need for later modules, to give students more of an introduction about what it's actually like to work as an aerospace engineer. We've got this Exploring Aerospace module. Now it's broken into 3 kind of case studies, and within that, each of them explores a different aspect of aerospace engineering. Now, you can mix and match the casework from this module from the different streams. So say, for example, if you're joining and you're not sure, you think aerospace, but maybe mechanical, maybe chemical, you could take one case from aerospace, one from mechanical, one from chemical. Now, if you decide you want to swap at any point, you can do that simply. So at any point in the first year, you can swap between any of the streams. And if it's swapping between mechanical and aerospace, you can do that at any point right up to the end of your second year. So if you're slightly unsure, this is a great way to, you can kind of join it within second year, you can kind of explore a bit more. And so in the second semester, you can explore a bit more and then make a decision. And which you cover in second year, I'll move through this a little quicker. We've got solid mechanics. So the ones on the left, semester A. Solid mechanics, so that's looking at how kind of structures respond to things. So for example, when you saw that video earlier of the internal kind of beams within the wing kind of bowing under the impact of the bird, it's understanding at what point materials break. So, for example, if you've got the titanium on the outer surface of a wing, how much impact can that take before it starts to tear? If it kind of pings in and deflects and bounces back to its original position, fine, we don't care. But at what point does it start to tear and rip? In which case you would have a very kind of dangerous situation. There's instrumentation and measurements. So that's the kind of science behind the fundamentals of how you monitor things, either in experiments or a kind of general monitoring system within a plane or any kind of engineering system. Spacecraft dynamics, now that's our first introduction to the kind of space side of aerospace. And that's looking at the kind of mechanics of space systems, both kind of maintaining stability of rockets during takeoff, but also the manipulation of how you kind of orientate yourself in space, say if you're adjusting things on a satellite. Now there's aerothermodynamics, which is a very long name, but essentially means supersonic flight. Now what that comes in is the physics of how a plane operates at subsonic speeds, so lower than about 330 meters per second, is quite different to how they operate at supersonic speeds. You need to have a lot of different design constraints because you worry about the shock wave, you're worried about the great heat you can generate during supersonic flight. So we do cover supersonic flight. You'll also see on the bottom right, there is subsonic aerodynamics. So this is the real kind of fundamental understandings of how a plane works, how a wing works, what are the design constraints when developing, designing a plane. There's but above that is numerical methods and data science within engineering. So again, it's quite a long name. Essentially, this is a maths module. We tried to make it as applied as possible. So it again involves some computer programming. It's the first steps that you would take on your way to learning how to do computer programming, like we saw that simulation with the bird striking into the wing, or indeed the flow simulations of, say, the wind flow past that wind turbine or of the Formula One car. Above that is control systems. So this is a huge thing within any kind of type of mechanical or aerospace engineering. And it's essentially how you design controllers. Now, where that's most relevant in aerospace is kind of maintaining stable flight. Now, that could be the control system used to control a drone, make sure it's got a stable flight, and that's, say, for example, a quadcopter. Or it could be just within kind of civilian aviation to maintain a stable flight of your kind of passenger aircraft, whatever. And lastly, you've got designing for sustainability. So this is, again, it's a furthering on of design, and we might have discussed previously about how big the number of jobs within design within aerospace are. And it's also linking that in with kind of sustainable engineering. So how do we make sure it's both environmentally sustainable, so using kind of good materials, understanding what sometimes is it better to use kind of, say, ones that slightly damage the environment but don't need to, but are less likely to lead to failure? How do you weigh that up? How do you weigh up the kind of environmental impact over the lifetime? So, for example, if something's slightly damaging to build, but it leads to lower emissions, kind of understanding those sort of choices that would affect engineering design. Now, in your third year is a little different. You've got a bit more choice in what you choose. Now, in this case, you take 3 modules per semester, and then you do 1 individual project that runs across the both semesters. So I'll talk about the modules first, and then I'll come back to the project. Now, first we have aircraft design. So again, that's making the kind of design element a little more applied, looking specifically at kind of aerospace problems. Then this next is engineering simulations. Now, again, this is where you start to learn the ability to kind of develop these computer simulations, like we saw with the bird strike or the faster wind turbine. Again, it's huge skill for aerospace in the kind of the modern market. So this is where you start to learn that. We also get flight dynamics and stability. Now that is a kind of follow on from the control systems module you would have taken in 2nd year. So this is again specifically honed in on maintaining stable flight. Now, you've also got some choice then. You can do kind of a more advanced kind of module on supersonic flow. So a lot of the students who are quite interested in kind of defense applications might take that because they're quite interested in the supersonic applications. Then there's also spacecraft design. So again, that would be students are quite interested in the kind of the space aspect of it. Again, you've got another materials module. So materials is one of the kind of key research strengths within our school, because we also have a material science degree program. And this would be kind of looking at materials, but with a specific application to aerospace, because aerospace has some particularly niche needs. So again, it's trying to keep things cost low, particularly getting really high strength out, but really low weight. Next is aircraft structures. So again, is once you've got the material, how do you design it? How do you employ it in the best way to kind of keep weight down, get that strength up? And then we've also got aircraft propulsion. So that could be kind of your kind of jet engines and your propeller systems. Now, a little bit about student projects. So in your 3rd year, you take a group project, or sorry, an individual project. And in your 4th year, there is a group project. That's if you're doing the master's in engineering. So we always try and match the project to students' interests. And in the current system, you get to, there'll be a list up online and you can apply for which ones you want. And we always try and match it to the students' interests. So for example, if students are interested in defense applications, they might want to look at a supersonic project. Other students have become fascinated with, say, design elements of it, sustainable energy or whatever. They can be either experimental or computational, so either doing experiments with wind tunnels, or they could be doing computer simulations. If it's more, say, for aerospace materials, it might be developing materials within the materials labs and testing them for the strength or durability or whatever. Or if it's design projects, design is probably the most popular among students. So just a couple of examples here we've got. So this is a student his project was looking at the effect of car shape on the kind of the drag or the kind of air resistance. So again, you would have come up with this computer model, had it 3D printed and installed it within the wind tunnel. So there's currently a group of students are doing a project looking at the kind of aerodynamics of trucks and different methods you can to kind of reduce the air resistance on that and save fuel. Some students are quite interested in the flight simulator, so you get an opportunity to use that in 2nd year, and then they decide to continue on with that in their 3rd year project. There's also some of the students this year in their 3rd year are going to be developing and designing their own flight simulator. And then there's a series of projects on the supersonic flow. So it would be kind of either computer simulations or experimental work using the supersonic systems. A lot of our students are quite interested in Formula One. So there's a Formula One student society. And a lot of students that are in that society choose to then do a project related to Formula One. So this is a large model of Formula One. It's about maybe like 60 centimeters long. And this is placed in the subsonic wind tunnel. Now, what this student project was interested in was understanding how the airflow past the airflow kind of flows over this design of the Formula One car. Now, what you would probably be looking at in this application is so what they've done is they've painted it with luminous paint. Before it's dried, they place it in the wind tunnel at high speed. So the air moves over and the paint kind of streaks along. And you can see some streaking kind of at the side or at the bottom plate. You then take it out and allow it to cool and to dry. And then what you find is you look over and you find where you start to get pools of paint. What that means is the airflow has kind of come in and sort of stagnated. Now you might then feed that back to your design engineers, say that another student you're collaborating with. And that would be an indication of, okay, if we're getting stagnant air there, that means stagnant air means high pressure, that high pressure is pushing us back. That's an inefficiency within design. You might try and kind of move to improve upon that. For the master's projects, these are always done in a group, and they generally involve a combination of computer simulation, design, workshop building, experiments, and field testing. So just a couple of examples. So this is the project done with the UK National Bobsleigh team. So they've got this is this combination of this is kind of wind tunnel testing that was done. This is the wind tunnel at BAE Systems at Wharton, and this is the actual kind of bobsleigh that would be used in the Olympics. And this is some kind of visualization they did with that's the actual one of the bobsleigh drivers, and they're kind of spraying some smoke in over it, and then looking from that video to work out how that smoke moves over and how the design could be optimized. There was also some recent projects looking at developing rockets. So this was to be entered into a rocket competition. Now, in this case, this is back from about 8 years ago. And this is the system they entered. It was fully monitored, so it had various sensors in it, your altitude, your velocity, your temperature, your pressure, all this stuff. So developed it, fired it off, and then did the data analysis of it. So again, it involves a classic combination. They would have done some computer simulations to kind of predict its behavior. They would have the actual building, work of constructing, the design, obviously putting it together, kind of field work testing of kind of buying it off, measuring it, and analyzing the data. So
launching in 5, 4, 3, 2, 1, launch.
That's the system firing off. Yeah. And just we'll play that in slow motion. You can see that flying off. And that's it flying off in slow motion. A little bit now about careers and opportunities for after you graduate. So the map shown here on the right is all the different kind of aerospace companies within the UK. You'll see there's a huge, UK and Ireland rather, there's a huge cluster around London. And each of these numbers, I'm not sure if you can kind of make them out, but that's the number of direct jobs within the space sector, the defense sector, or within the kind of aviation sector. So there's a huge number of jobs. So these statistics are from 2020. So the UK aerospace industry is the third largest in the world. It's the second largest in Europe. So it's got over 1,100 companies, and that's over 385 skilled direct jobs. So that does not include, you're working for Boeing, but you're doing, say, cleaning work. It doesn't include contractors. It doesn't include someone who works for a company, but they do kind of 1 week's worth a year for Boeing. All of these are really skilled jobs for aerospace companies. Within the space sector alone, there's over 47,000 jobs. So this overall, they contributed almost 80 billion to the GDP of the UK. And the average wage in the aerospace sector is over 40% higher than the UK average. Some examples of some of the jobs that our graduates have gone into. Some have gone into use this to kind of help with their application to become pilots, either within the military or within kind of civilian aircraft. So in this case, British Airways on the right. Some of my students really enjoy the research projects that tend to stay in research, either doing research masters or sometimes PhDs. Now, a little bit about the graduate jobs. So how you kind of class a graduate job and how you estimate the price varies a little, but these statistics are from 2020 as well. So the average salary for a graduate in the UK was about 23,000. An average salary for someone who'd done engineering was about 27,000 to 28,000. So right from the moment you kind of get your first job, you're likely to be earning more with an aerospace degree than any other type of degree. There's part of the reason for that is that engineering in general is a high paid job. Also, the engineering graduates are in high demand for a lot of other sectors such as consulting, finance, digital IT, management, and defense. Now, why is it that engineers are in such high demand? There's two real factors. So one is that maths you've been building up throughout, the maths and the computer coding. They're applicable to a wide range of areas. So that's a really great skill to have. And the other thing that really sets engineers apart from, say, physicists or some other type of scientist is that engineers are problem solvers. So it's not just that you set out to do a project to really understand something, it's that you set out to kind of make something better. For example, if you're doing a design project, it's not that you're just trying to understand one problem, it's you're trying to understand it and fix that problem, come up with solutions. That's why the engineers are in such high demand for things like project management and some various other kind of really high pay sectors. To help with industry placements, so that could be if you're doing the year in industry, or it could just be somewhere in internships. We have Monica, our industry placements officer, who can help connect you with jobs. So we have a whole series of companies we have connections with. Now, all these positions are paid. We don't do any unpaid positions. So some of these companies that we've students have done placement with in recent years, some of the kind of big beasts within kind of aerospace within the UK, so General Electric Aviation, Rolls-Royce, Airbus, BAE, and then a huge number of other kind of smaller companies within aerospace, so some airlines, some kind of airports, some companies like, say, for example, GKN or kind of Altair, who do kind of support work for, they'll be involved with little specific aspects of, say, the design for a larger company like Boeing. There's also, we've had a lot of placements within the automotive industry, so Toyota, Rolls-Royce, Vauxhall. There's also, we had a student did a placement at the Formula One, the Williams team, and some of our students recently, just over the summer, did a site visit for a couple of days with some of the lecturers here to the Aston Martin team. And in general, over the last couple of years, we've been connected with 112 companies here, so I've only shown about 20 of them here. And that's that. That's the end of my talk. So my name is Neil Cagney. My email address is up there. So I'm happy to take any questions now. If you can think of a question afterwards, then you can always get in touch with me this way. But yeah, happy to have a look at any questions within the chat. Okay, I can see that there's no questions in the chat. So I guess we can leave it there. But yeah, thanks a lot for attending. I hope to see you all at the Offer Holder Day events, or indeed at in some of the lectures next year. Thanks a lot for watching.